All right, welcome back to what I'm going to be calling part 2, since I had a malfunction in my smartboard and it canceled out my last video. We pretty much got all the way through problem number 2, except for the very last question that had to do with an agent who spends an average of 24 minutes with each of the potential customers. How many policies would we expect the agent to sell? So I still have the residual plot on my calculator, even though with whatever the malfunction was, it deleted everything that I had written for the problem. And so on my calculator, I also have the regression equation saved in y equals. So if I want to determine the expected number of policies to sell, we know that 24 minutes per customer is going to be an x value. So if I let x equal 24, there are several different ways that I can plug this in to determine the value of y, or predict the value of y. I can do this in my table. If you go to your second graph, you can look at your table and you can actually just scroll down until you see 24. But that can be tedious and inefficient. So another way would be to look at your graph. Now, if you remember, I have the residual plot, so it's going to be a little bit harder for me to figure out the corresponding y value, since my original scatter plot is no longer there. But I can also use function notation. So just like we did when we were constructing the residual plot, if I go to vars, y vars, and choose the function where my equation is saved, I can basically evaluate the function at 24. And that gives me another alternative for predicting for y. So I know that my y hat, remember to put a hat on it, is going to be 11.451, and that would be policies. And that's what I expect or predict from that value. All right, and number 3. So now you're given summary statistics, and you have to be able to come up with a regression equation based on those summary statistics. So it basically says a random sample of 30 U.S. farm regions surveyed during the summer of 2008 produced the following statistics. So we know that the average temperature during the growing season is 81 for the mean, and then with a standard deviation of 3. And the average corn yield per acre has a mean of 131 and a standard deviation of 5, and we know there's a correlation coefficient of 0.32. So it asks us to state the explanatory and the response variable. Well, I expect that temperature is going to influence the corn yield. So I would expect that my x variable, or my explanatory variable, is going to be the average temperature during the growing season, and that my y variable, or my response variable, is going to be the average corn yield. Okay, so it asks to determine the slope of the regression equation. So remember, the slope is going to be the correlation coefficient times the standard deviation in y over the standard deviation in x. So just make sure that you've got your x and y sorted, so we know that the temperature is going to be my x and the yield is going to be the y. So to determine the slope, my correlation coefficient we know is 0.32. The standard deviation in y is going to be 5, and the standard deviation in x is 3. When I multiply that out, I'm going to get 0.533. Let me actually do that on the calculator, though, so that I can store all of those decimals, because I do expect accuracy. So I don't want you to round until the very last step. So I'm going to go ahead and store that value in my letter A. Okay, and so in parentheses, I'm just going to put a little letter A as a reminder to myself that that's where I stored it. Now it asks me to calculate the y-intercept. So the y-intercept, remember, is going to be the mean of y minus the slope times the mean of x. Well, the mean of y I know is 131. My slope is 0.533, and the mean of x is 81. And again, I'm going to do that on my calculator. 131 minus, actually I can just do second answer, and that'll call up my previous answer, and then I want to multiply that by 81. And so my y-intercept is 87.8. Okay, and that I don't need to worry about storing that anywhere. So it also asks me to interpret these values in the context of the problem. So be very careful when you're interpreting. So for the slope, it's as x increases by 1. Well, x has to do with the average temperature during the growing season in degrees Fahrenheit. So for every degree that the temperature rises, or that the average temperature rises during the growing season, I expect an increase in 0.533 bushels per acre of corn. My y-intercept then means that when the average temperature during the growing season is 0 degrees, then I would expect 87.8 bushels per acre of corn to be yielded. Now, the y-intercept in this problem may not make any sense because I'm assuming that the average temperature during the growing season in the data that I collected was never 0. So the y-intercept may be an example of extrapolation, but it's impossible to tell without the actual data. Letter C asks to go ahead and write the equation of the line, so just remember to put a hat on it. Y hat is equal to 0.533 x plus 87.8. And then it says, based on the study, what is the mean predicted corn yield for a region where the average growing season temperature is 76.5 degrees Fahrenheit? Well, that's an x value. So if I let x equal 76.5, then I want to predict the corn yield. So in my equation, now remember, my slope I stored in letter A. So I'm going to want to go ahead and call up letter A now because I don't want to have any rounding issues. And I want to multiply that by 76.5. And then add that to my y-intercept, which I didn't have to worry about any rounding issues there. That's easy. And we expect 128.6 to be our average corn yield per acre. So that would be bushels per acre. Or I guess I should say average bushels per acre. Okay. All right, in problem number 4, it says many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? To investigate, an AP statistics teacher randomly assigned students to seat locations in his classroom for a particular chapter. At the end of the chapter, he recorded the row number, where row 1 is the closest to the front, and the test score for each student. Least squares regression was performed on the data. A scatter plot with the regression line added, a residual plot, and some computer output for the regression equation are shown below. So if you look at the original scatter plot, so this is the original data. I'm just going to kind of look at this problem before answering some of the questions. When I look at that scatter plot, I do not see an association between the variables. They're very scattered about. So I'm not even sure that it warrants investigation in terms of determining a model. But we have the information available to us, so we're going to answer the questions anyway. So in letter A, it says, what is the equation of the least squares regression line that describes the relationship between row number and test score? Define any variables that you use. Okay, so if you remember from the output, we're really only going to be focusing on the coefficient column. And remember, the number that is next to the word constant is always going to be your y-intercept. And then the row, that's going to be our x variable. The coefficient of our x variable, obviously, is going to be our slope. So I would say that y hat is equal to negative 1.1171, that's my slope, times x plus 85.706. Now, it does say to define any variables that I use. So x is going to be the row number. That's my independent or my explanatory variable. And y is going to be the test score. And that'll be my response variable. It says to calculate and interpret the correlation coefficient. Okay, so I'm not given the r value in the problem. We're given, though, r squared. So we are told that r squared is equal to 4.7%. So what you're going to need to do first is change that to a decimal. So that's 0.047. Make sure you move the decimal point 2 places to the left. And then to find the value of r, I'm basically going to take the square root of that. I do need to be careful though, because the correlation coefficient should have the same sign as the slope. And since the slope is negative, I know that my correlation coefficient must be negative. There's nothing in the problem other than that to remind me to make sure that my correlation coefficient is negative. So that's something that you're going to have to remember to do. So if I take the negative square root of 0.047, I get a negative 0.217. And it says to interpret the correlation coefficient. So obviously it's negative. So there is a negative. And since this value is very close to 0, I'm going to say weak association between row number and test score. And then from the scatter plot, I think it's pretty clear that we wouldn't really want to model this using a linear equation. But it's just asking us to determine the correlation coefficient and interpret it. So this is good enough. So there is a negative weak association between row number and test score. You can't really say that as the row increases, the test score decreases, because it is such a weak association. In part C, it says, is the line an appropriate model to use for these data? Explain how you know. Well, there's 3 things you can look at. You can look at the original scatter plot, and on your AP exam, you want to make sure that you're providing enough justification for any claim you make. So make sure when you're using your explanation that you go back. So I know, for example, my correlation coefficient is close to 0. My R squared value is 0.047, and if I look at the original scatter plot, it doesn't make any sense to model this with a linear equation because there's so little relationship between the 2 variables. I think that R squared is the area where most students struggle, so let me go ahead and just write out how I would explain whether or not the model was appropriate using R squared. So I would say, since only 4.7% of the variation in Y, which in this case is the test score, so since only 4.7% of the variation in test scores can be explained by the linear regression equation on row number, a linear model would not be appropriate. To model this data. You could say something like, clearly from the scatter plot, there is no association between the variables, and this is confirmed by the correlation coefficient being so close to 0. Okay, and the very last problem, this gets us looking at linearization. So number 5 says, a startup company has developed an improved electronic chip for use in laboratory equipment. The company needs to project the manufacturing costs, so it develops a spreadsheet model that takes into account the purchase of the production equipment, overhead and raw materials, depreciation, maintenance, and other business costs. The spreadsheet, which isn't shown, estimates that the cost of producing 10,000 to 200,000 chips per year. And then you're asked to consider the scatter plots below. Well, if you take a close look at the scatter plots, if I look, for example, at the first one, notice that it says chips produced per cost per chip. Whereas if I look at the next one, notice now I'm looking at the natural log of the chips produced versus the cost in dollars. So if I think of my X variable as being the chips produced, and my Y variable being the cost of the chips, then this first scatter plot is comparing X and Y. The second scatter plot is comparing the natural log of X versus Y. If you take a look at the third scatter plot, now we're looking at the natural log of the chips produced versus the natural log of cost. So now we're looking at the natural log of x versus the natural log, natural log of y. And then the last one, it's x versus the natural log of y. So this is an example where we're looking at linearization. So I'm interested in the graph that produces the straightest line relationship. One of the ways that I can tell is if I look at my r squared value. Remember, the closest that value is going to be to 1, the more straight the relationship is. So even though I can clearly see that this graph number 1, and it looks like graph number 4, there's a definite curve. But in terms of the second and third graph, it's a little bit harder to tell which is more linear. So I want to look at the numeric representations, or the r squared in this case. And so this graph right here has the r squared value that is closest to 1. Obviously, if I take the square root of these r squared values, I'm going to get the correlation coefficient, and I would expect that when I take the square root of 0.9945, it's going to be closer to 1 than any of the others. So when I think about this relationship, the natural log of x versus the natural log of y, log means that I want to model this with a power function. Okay, so the most appropriate regression equation would be a power model. So question A says, which of the following regression models should be used to predict the cost based on the level of production? So here, since I already know a power function is going to best model the data, because when I look at the natural log of x versus the natural log of y, it linearizes the data. So now I just have to pick the power function equation. Well, in the first one, this is clearly a log equation, so I know that's not going to be appropriate. In number 2, well, this is a linear equation, so that's not appropriate. In the third one, notice that I have an x in the exponent. This tells me this is an exponential model. That is not appropriate. And so in my very last one, I have x raised to a power. This is a power function. And so this last model is going to be the regression equation that is going to best represent the original data, even though we can't see the original data. And so each of the equations that's given is a possible regression equation, but option 4 is going to be the best because of the linearized relationship between x and y. It says to use your model to estimate the cost of producing 30,000 chips. So I'm basically going to let x equal 30. I think it's in thousands, it would make sense. Well, when I look at the scale on the x-axis, it makes sense to say that x is going to be 30. So to predict for y, I'm going to have 473.06 times 30 raised to the negative 0.502. And so if I do this on my calculator, I get 85.783. Or I guess since this is in dollars, I can just round to 2 decimal places. So I would expect that the average cost per chip would be $85.78. It asks to calculate the residual. So to calculate the residual, remember, we do the actual minus the predicted y value. Well, the actual cost was 85.75, and I found the predicted value to be 85.78. And so when I calculate the residual, it's going to be a negative 0.03, and that is in dollars. So my prediction was 3 cents too high. If the company wants to keep costs under $50, is it reasonable to use the model to predict the number of chips it should produce? So algebraically, if I want to keep costs under $50, basically I would let y equal 50, and then I would figure out the intersection of the two equations. However, if you think about this, we said that the chips produced was the explanatory variable, and the cost was the response variable. So even though algebraically we can solve this problem, that's not the intention of the regression equation. And so when it asks you a question like this, is it reasonable to use this model to predict the response, the explanatory variable, the answer is really no. We shouldn't do that. We can, but we don't want to be very confident in our results because we stated ahead of time that the number of chips produced was our explanatory variable. So we don't want to use the equation and reverse the relationship between the variables, because that's not what the equation was intended to do. So like I said, we can still do it, but it's not appropriate since we don't want to predict for our explanatory variable. And I'm running out of space. Okay. And then it says the company is increasing its production to 0.5 million chips. Estimate the cost, and how confident are you in this prediction? So 0.5 million, that would be 500,000, really. And so if I let x equal 500,000, that means I'm letting x equal 500. So, So I can certainly plug that in. So 473.06 times 500 raised to the negative 0.502. And if I plug that into my calculator, I get $20.89. And I can tell from my original scatter plot, the highest value that x takes on is 300. Actually, in terms of my data, it looks like 200,000 is the highest value that my data has. So to make a prediction when x is 500,000 is too far beyond my data. I don't have any data to support my model at that point, so I would not be very confident in this prediction. This is considered extrapolation. So we don't have data to support our model. Beyond 200,000 chips. So we're not confident in the estimate. Okay, and so that is essentially everything you need to know for the chapter test. I hope this was helpful. Sorry that it spilled into two different videos, but I hope this helps, and I hope you do well.